Hello, everybody. Welcome back. We had an amazing design review on this preamp board on layer 3 and how it could be optimized, including how it connects to layer 2 and layer 1 of the PCB. Now we are approaching where we talk about layer 4 on the PCB. And if you haven't seen the rest of the video series, please check those out because everything is connected. Thanks so much, Dan, for doing the review, and please take it away.
All right, welcome back, everyone. Just a quick recap. We spent some time in the last segment talking about how to optimize layer 3. Layer 3 is a very powerful tool. It's next to layer 2, which is a solid ground plane. What we talked about were ways to modify the routing on 3 to improve the opportunities for layer 4, because layer 4 is not next to layer 2. Layer 4 is 2 dielectrics and a signal layer away from ground. So it's what I call an orphan layer, and it has to be routed as if it was a single layer board for the most part. In our design here, because we are going to be able to optimize layer 3, and if you want to pop 3 back up again, please, Hirsch. We have ground flooding and power islands on 3. We want to change the shape of the power islands so that they only go where there's vias. And then we want to extend the ground flood into those spaces. And then along the edges of the ground flood, we want to connect those with vias to the ground on layer 2 to basically build an escarpment where the ground on 2 is brought up to the ground on 3, so that you've got this solid structure as far as the fields are concerned. So we've extended the ground plane on 3 to a space on layer from 2 to 3. Now what we can do is on layer 4, use those ground islands to help improve the signal integrity that we can achieve. The first thing I want to say is every single via here and trace on layer 4 absolutely has to have a ground transition via next to it, because these signals are coming from either layer 1 or layer 3. Their dielectric is not connected to the dielectric between 2 and 3 and 1 and 2. These signals are routed on layer 4, and the dielectric between 4 and 3 is not directly connected to the paired dielectrics in the space 1, 2, and 3. So every signal via on 4 requires a ground transition via, so that we connect the horizontal dielectrics between 1, 2, or 2 and 3 to, in this case, the coplanar dielectric on layer 4. Because in this case, except where we're going to be able to show you how we can use these ground islands on 3, you're depending completely on the coplanar transmission lines you're creating, which is going to the signal with ground flood next to it. So you want to create a discrete space for these signals, and it's going to be between the edge of the foil on the trace and the edge of the foil on the ground flood. So that's the foundation of a good behaviors for layer 4. You're not going to be able to do controlled impedance. You're not going to be able to do high-speed signals, but you will have problems with immunity, and you can probably have problems with radiation, all because these signals, these traces, are not properly connected to the foundation of the board. So first improvement here is every place there's a via going to bring energy to layer 4 requires a ground transition via. The first thing that has to happen. The other thing is that same thing we saw on layer 3. There's a lot of ground flood here, and this is the comment for layer 1 as well. All of these ground flood spaces need to be connected to the ground plane on 2. So this is going to require stitching vias around the perimeter of these shapes in order to connect them solidly to the space that's created in the 1, 2, 3 spaces. So that would be the next thing to do. And then there are power islands on this layer as well. These power islands, if they're adjacent to power that's the same power signal, power conductor on 3, are not doing anything. If I've got 5-volt analog on 3 and I've got 5-volt analog on 4 on top of it, that's the same conductor. There's nothing happening in the dielectric between 3 and 4. I don't want to waste dielectric. You have to start thinking the conductors, the copper, is not the main part of the PCB. It's the dielectric. We want to be able to use these wherever we can. So if I really wanted to have 2 dielectrics involved in the power distribution, then I would want to make the layer 4 copper be ground if I'm going to use the layer 3 copper as a primary conductor. Then I've got 2 to 3 power and 3 to 4 power. So it's power, it's ground, power, ground. 2 dielectrics that I can use for moving the energy. It's not for storing energy, it's for delivering energy. It's about impedance, not the femtocoulombs of charge that's in that space. I never, ever care about planar capacitance because there's no energy there. And it takes so long to get whatever's there that it doesn't matter. It's got no impact. So all these places, where your cursor's at is a good place here, Kirsch. There's power vias in the right-hand side of that shape that he's got his cursor next to. There's the power structure. This is a ground flood. All these power vias here, they're not helping anything because there's no good way. All those power vias need to see the ground vias that are there next to the cursor. They are going to find their way down. So if I really wanted to bring this energy from 1 or 3 to 4, I would want to put a ground via next to each of these power vias. So right now, this structure is really not helping me at all. If I need it to connect vias, because I can't connect them on 3, then I'm going to have to be very careful how I route this, especially if it's going to need power. Then I'm going to need to make sure that I have a power via going through the board stack that's going to connect the power on 1 to the power on 3 to the power on 4. But next to that is going to require a ground via so that I'm bringing the energy that's in the horizontal dielectrics into now, unfortunately, the coplanar dielectric, which is really a wimpy one, but it's there. So if I needed to bring this energy, so right now I've got 2 traces that are showing on layer 3 that are breaking up the structure. So if this was, zoom out a little bit, please. So this is a power structure horizontally here. And it's adjacent to power on 3. Except I've got these traces in the middle. If I'm using this to connect the power on 3 from the left to the power on 3 to the right, the only way I can make this work well is if I have ground next to the power. So I've got it there. They've got kind of a ground thing up above it. Where I cross these traces, I need to put a via on each side with ground. So I want to build a bridge. I'm trying to bring this, I want to try to keep this signal in the space between 3 and 4. This really, in my estimation, needs to be ground flood. And so that I've got the dielectric between 1 and 2, 2 and 3, and then I've got the 3 and 4 dielectric because there's now ground. And then where I move from the space between 3 and 4, I have to get past this split. So at that point, I would put 2 vias and a ground copper next to this so that I build a short bridge across these traces and bring it back down to the power on 3 across and then back up and another one, because in order to get the power across this space where this is broken, I would need a stitching via. So if I made this ground and needed to move power from the left to the right, I would put a trace in next to this. It would be just a short power connection that would be the bridge across these traces. So the energy would be in between 3 and 4 to the space between 4 and 4, the coplanar space, to another via, back into the space between 3 and 4, over to the next split, back up to the space between 4 and 4, and then back into the space between 3 and 4. It would be a discontinuity, but a lot less of a discontinuity. Again, this copper is not doing anything of value. I mean, even if I needed to connect the left and right halves of this layer 3, there's no good path for this energy. So it takes more wave cycles to move energy from point to point, and every time it's moving, it's having to spread out over the whole board structure. So you're increasing crosstalk, increasing the time it takes for the field to move. It's a larger volume of space, so it takes longer to fill and discharge that space. So a lot of things happening there. So again, when you're trying to route things on 4, you're primarily concerned with coplanar ground structure. And if it's going to be power, you know, the edge of the foil to the edge of the foil is really high impedance. So by throwing more power copper on top of 3 and still breaking the space didn't solve any problems. Because again, the fields can't go through copper. The only way they get around copper is the E field changing causes the H field changing, which causes an E field to change. So that crosstalk, which is the E cross H conversion that happens as the energy moves through the spaces, is critical. So let's zoom out again and just have a little more of a discussion. It would be great if we could have this board, modified and do some discussions again. So looking at this, we've got a couple of power structures here, and we've got, they're probably the same. Looks like they're repeated on 3. If you have the same copper on 4 that you have on 3, you're wasting that dielectric. If you really want to take advantage of the way the board's face, I would have eliminated, I would make all these two shapes, unless there were 2 different power supplies, I would make them ground, and then make sure that I could connect on 4 across these splits that I'm having to route these traces on layer 3. Again, bring the energy so that it's between 3 and 4 into the space between the edges of 2 conductors on 4, back down into the space with vias between 3 and 4, back up with a couple of vias to 2 conductors across the split, and then back down in and around. The other thing you can do is look for ways to maybe route these traces someplace else. And then the same thing is, if these become ground, then this ground flood gets better. There's this little split here where you've got a peninsula going up between these 2 power shapes. Down in the middle, that kind of a zigzag looking piece there. No, the little teeny trace shooting up between to the right. No, in the little grounds, the ground is sticking up between it right there.
This right here.
We've got another peninsula sticking up there. Either eliminate it or drop vias in there. Again, ground flood is there to fulfill a purpose, and we want to make it effective. Again, if you don't have this tied to the ground structure of the board, then you've created antennas or paths for increased crosstalk. So again, thinking about the behavior of the fields, it's constant, it's simple. A changing E field creates a changing H field in the conductors that bound it. If one of those conductors is a trace, there's a fixed amount of magnetic flux that's created on each of those conductors. The flux density resulting on a trace is much higher than the resulting flux density around a plane. But the total flux in each of those conductors is the same. So when I have a piece of copper floating up in the middle here, any changing E fields in the space between that conductor and another conductor is going to cause a changing H field in that piece of copper. The smaller it is, the higher the flux density that's going to result from the changing E field. That will then cause a larger changing E field in the adjacent space. And the other thing we haven't talked about, especially on the outer layers, is when you properly use the flooding on the outer layers and you stitch them to build this pseudo Faraday cage, that you present, especially in ESD testing, a larger surface area for this bubble of charge to see, because it wants to, again, create the lowest impedance driven by surface area. So the field of the ESD impulse is going to be distributed across these larger surfaces. So the resulting E field, because it's going to create an H field on these pieces of conductor, it's going to reduce the magnitude of the changing E field and helps reduce the impact of these ESD events on the system itself, reduces the chances of damage to the devices, reduces the chances of causing disruption in functionality. And these are, again, using your copper to do the job that it's capable of doing. And we haven't added any components. We just correctly use the components we're buying. And typically the most expensive, least thought of component is the printed circuit board. It is the absolute most critical part that you do. It's the only truly fully custom part that you're buying. And we are taught the wrong thing about printed circuit boards. They are dielectric structures and not copper. The copper we use to create the spaces that are the dielectric. Your product in the case of a 4-layer board is the dielectric between 1 and 2, 2 and 3, and 3 and 4. You've got 3 wonderful dielectrics in there. And that's where your energy gets delivered. And you want to focus on, how do I use these dielectrics properly? And we do that by developing copper structures that define 3-dimensional spaces that we use to direct the energy. So let's zoom out once again. Again, 4-layer board is a very popular and very powerful board stack, but you have to realize that if you have ground on 2, that you are going to need to be very careful with how you route layer 4. I've seen some discussions where people want to do 2 ground planes in a 4-layer board stack, and they go signal, ground, ground, signal, or they go ground, signal, signal, ground. I would never waste dielectrics. If I was going to put 2 ground planes in here, it would be signal, ground, ground. And then which is what I'm trying to do here. All the ground flood on 4, we want to use to possibly create the use of the dielectric between 3 and 4, so it acts as if it was another ground plane. So that's the idea. Taking these several lessons that we've tried to present to you, and using that approach, not just on this board, but on your product, can make a really, really big impact on both the manufacturability, the power consumption, your EMC behavior. All these things will help improve your chances of having first-time compliance, because you continue to remember it's all about the space. Thank you.